So, hello and welcome student to today's talk. So, this is our course MA425 Topology. Okay, and this is lecture number 13. Okay. Now recall in our last class we have discussed that the product topology on R omega is actually metrizable. It's coming from a metric, right? That we prove it. And the natural question one can ask whether every topological space is metrizable. The answer is no. It's not true. Okay. Maybe today we will discuss one such example. But before that, we need to know some of the properties of this symmetric topology. Okay. So let us start. So our theorem. So theorem. So suppose that you have this x tau x and y tau y and two topological spaces such that these topologies are actually induced by some metrics, so that tau x and tau y induce by some matrix, say dx and dy respectively. Okay. So then in this case, if you want to know function, then the following are equivalent. So in this case, the following TFAE mean the following are equivalent, right? So the following. So in this case, the definition of continuity you can replace by the metric itself. So number one, a map f from x to y is continuous. Okay. And number two, because you have a metric, you can talk about this thing for metric, right? So what does that mean? This means for any x belongs to x and epsilon positive, there is this delta positive which depends on obviously epsilon, such that what happens? Such that that if d of x y less than delta, this implies dy of fx fy is less than epsilon, right? Or in other words, you can say that if y belongs to open ball, oval epsilon delta ball, that is, you can say that if y belongs to this open delta ball, so when I am writing ball with respect at x, I mean that with respect to this metric dx. Okay, this implies this image of y, f of y, is actually belongs to the open ball centered at f of x of radius epsilon. Okay, and this is with respect to the metric dy. Okay, this is the meaning. So these two are equivalent actually, and obviously the proof is also not so difficult. So let me first prove 1 implies 2. Proof 1 implies 2. So that means I'm assuming that the usual definition of continuity at topological spaces, right? So it pullback of open set is open, and then I will prove that it satisfies the epsilon delta definition, like y belongs to this if y belongs to this. Okay. So why 1 implies 2 means I already assuming 1. So let x belongs to x and epsilon positive. Okay. So now you consider, so this is given, this is for any arbitrary x and epsilon. Okay, so now consider that epsilon neighborhood, say b of fx. Okay, so this is obviously open neighborhood, open balls are open neighborhood, right? This is with respect to the metric dy. Okay, this is a this neighborhood of fx, right, which is open set. So thus what you can say, that the inverse image of this is open, right? So that is the definition of continuity. So if inverse of this b f of x epsilon is open in x, so that means this is belongs to the tau x. Okay, so now if it is belongs to the tau x, and this is not only that, this is actually neighborhood of x, right? Because if x this is continuous at that point. If something is continuous, means continuous at every point. So if it's continuous at the point x, so the pre-image of open set contains that point itself, right? And this is open set means what? Is the open balls are epsilon balls, are whatever open balls are there inside the topology, they form a basis, right? So every open set contains a basis element, contains that point. So thus therefore there exists delta positive such that you have a basis, right? So it's b x delta, this is inside f inverse of b f of x epsilon. Okay, so this is dy and this is dx with respect to, and hence done. So this means what? This means f of this b of f of b of yeah, so f of b of x delta is actually subset of b dy of f of x epsilon, and this is what we want to prove, right? Whenever y belongs to this, and then y is subset of this, and hence f of y, it belongs to this set, right? That is exactly what we want to prove, that if y belongs to b x delta with respect to the matrix dx, this implies f of y belongs to b f of x epsilon with respect to the matrix b dy. Okay, so this is exactly condition to what we want to prove. Okay, and hence now conversely 2m plus 1 also is not so difficult. So now 2m plus 1, 2m plus 1 means that it is given that whenever x belongs to that y belongs to that open ball center at x, f of y belongs to open ball center at epsilon ball center at f of x, right? Now you need to show that pre-image of open set is open. Okay, now so let you start with the open set. Let b belongs to tau y is open set. Okay, and I need to show that, and our claim is that f inverse of v is actual open set in x, so it belongs to tau. This is the claim. Now to prove this is open set, what I need to prove? I need to prove that it contains the basis element, right? And now how to do, I mean, given a point and inside the set, then this must be inside the basis element, okay, for any point. Okay, so let x be a point. So let we choose x belongs to f inverse of v, it's point on that thing. So I need to find out open balls center at or containing x which is inside f inverse of b. Then I am done. Then that will implies that f inverse b is open inside tau x, right? This is the claim will be proved. Now if x belongs to this, then f of x is element of v, right? and we know that the function is continuous at x. Then what does that mean? That means for epsilon positive. Okay, so this is inside V. So what does that mean? That means there exists, obviously there is this V is open set inside this, so there exists some epsilon positive such that this there is open balls, say for example B f of x is epsilon. This is sitting inside V, right? Because V is open set, so you have open ball center at that points which is inside that open set. That is the meaning of V is open, right? It contains a basis element. And now using the definition, now using this epsilon delta definition, like whatever you assume 2 definition, there exists delta positive such that what happened? So you have a delta positive such that what happens? Such that you have the open ball bx delta. Okay, so these open balls is actually sitting inside f inverse of b. So this is with respect to x, b dy f of x epsilon, right? This is the definition. Okay. Okay, so that means so this is the definition that okay, so let me again show you. Yeah, so whenever y belongs to that, then if a y belongs to that, so what does that mean? That means that b of dx, this open neighborhood, open balls is sitting inside f inverse of this, right? So that is exactly true. Okay, so so then but you see that this x is actually inside this open neighborhood or open balls, this, okay, this dx, right? And this is a subset of V, and hence so f inverse of this is subset of f inverse of V, right? Because this open balls and epsilon ball center at f of x is inside V. Yeah, here. Yeah, this one. Okay, so this is inside f inverse of V, and thus f inverse of V is open set. That means it's inside the topology of x. Okay, so pullback open set is open, and that proves that function is continuous. So f is continuous. Okay, so what does that mean? That means when the space is metrizable, so the topology coming by metric, then the equivalent condition of continuity is you can give by the metric itself. Okay, so whenever you have distance between 2 points at the domain is less than delta, the distance between 2 points at the range is less than epsilon. Okay, so now we are going to prove one very important theorem, and that we call sequential criteria or sequential lemma, whatever. That will help us to check whether some spaces are metrizable or not. Okay, the question I asked in the beginning, okay, whether every topological space is metrizable or not. Okay, so so this is a very important lemma. It's called the sequence lemma. What does this lemma tell? This lemma tells that for arbitrary, okay, so let x tau x be a topological space and you have a subset something. Okay, so if you have a sequence xn is a sequence of inside A such that xn converges to A, then the x is nothing, x cannot go very far, so it has to be inside a closure. Okay, so till this part you don't need even any matrix, right? Because this we will show that this will prove for any topological space. So the limit of a sequence are elements of the closure that I said one of our these live classes, but today I am going to prove it. And the question is that what about the converse? Like if you have a point inside the closure of a set, does that mean that you have a sequence that converges to that point? The answer is this is not true always. This is true if the space is metrizable. I mean, let us assume that it is metrizable. You can assume a little bit less, but metrizable is enough for me. Okay. So, so the converse is true. Converse is true if x is metrizable. So what does that mean? That means the topology is induced from a metric. Then you say that that is, what does that mean? That is, so let me write down properly. That is, if x is metrizable, then for any x belongs to a bar, there exists a sequence inside A such that xn converges to x. This is the meaning. Okay. So the metrizable property tells you that every element of the closure of a set is actually limit of some sequence of the set. Okay. Okay. So the proof. Let me start the proof first. The first part is you don't need metric. So this is a property of topology that okay. So let me start with the proof. So let xn converge to x. Okay, and it is given that your xn's are elements of A. So now I need to prove that x is inside a closure, but by definition, by definition of this convergence we get what? For any neighborhood u of x, there exists some natural number, right, such that your xn belongs to u for all n bigger than equal to n, right? So what does that mean? That means the tail of the sequence belongs to that neighborhood u. What does that mean? That means that u, so you can always find out this neighborhood u, which is the u intersection a not equal to 5, right? Because xn is element of a and also xn belongs to u, and this implies that this sequence at that point x is a element of the a closure, because a closure means those points such that every neighborhood of that point has an empty intersection, right? Intersects with A. Okay, so this part is obvious, so this is not difficult. Now I need, if I assume the metrizable property, then that means I have a metric which actually induces the topology, right? Now the moment I have a metric, then I can easily construct a sequence which converts to the point x. Okay, now conversely, let x is metrizable. Okay, and the D is the corresponding metric. Okay, so this is, I got it. Okay, and now so let this x is element of that closure of the set X. Okay, so what does that mean? That means there exists, so this is inside the closure, and then I can talk about given for any positive number for any n. Okay, so you choose a neighborhood that neighborhood of x with the radius 1 by n with respect to the metric d, and you see that this is the neighborhood of x, and this must intersect with a. This must intersect with a because x belongs to the limit point of x belongs to the closure of a, right? So this intersection has to be this. Now choose that let xn belongs to this neighborhood. For every n you choose an element xn which is inside the intersection bd x 1 by n, right? Now if I choose this, then what happens? Then I will show that this is the sequence extends. Oh. So this sequence extends is element, obviously this is inside A, and I claim that. So claim this sequence extends. Okay, so I don't need sequence. I mean this is converged to, this is my claim. Okay. Now to claim something is converged to this, what I need. So I need to show that given epsilon positive, there exists. I mean, if you choose open ball, right? Open ball means here you can obviously you can choose open set means you can always choose open ball inside that. Okay. So the proof of this claim is what? So let you choose U, B, and neighborhood of x. Okay, so I need to find that U intersections there exists a natural number such that after that the tail belongs to that neighborhood, right? Now if you neighborhood of that, then you always know that you can have a basis open set that contains x and inside the neighborhood. Okay, so there exists some neighborhood, say B x epsilon with respect to metric B such that that is inside U, right? Now I will show that this epsilon ball contains actually infinitely many, or rather the tail of the sequence after some natural number, right? Now this is how do I do? So you choose your natural number n such that 1 by n is less than epsilon, and that you can always possible by Archimedes property, right? Because epsilon is positive, and then you can find out you can measure 1 with epsilon with the help of a natural number, right? This is Archimedes property. And for this natural number n, what happened? So thus whenever your n is bigger than equal to this n, what happened? Then this b d all those b d x okay, so this b dx 1 by n, this will be a subset of see n is bigger than this, means 1 by n is less than 1 by capital N. So this is subset of b dx 1 by capital N. Okay, and which is subset of b dx epsilon, because epsilon is bigger than 1 by n. And now you see that your xn's are inside x1 by n, right? These are all inside x b and this side. This is for all n greater than equal to capital N. Yeah, I already wrote it. So what does that mean? That means this xn belongs to b dx epsilon, and which is also inside U for all n greater than equal to n. And this thus this implies that xn is converged to x. Okay, so this completes the proof. Okay, so what do we prove? That this kind of sequence lemma tells you that if you have a sequence that converges to a point, that point belongs to the closure of the set. But converse may not be true. You just find out example, homework, that it's not always true. Okay, maybe I will give you one example. Okay, immediately. And if the phase is metrizable, then obviously converse is also true. That means given any point inside the closure, you have a sequence of points of that set which converge to that point x. Okay, and this is going to help us to prove that that there exists space which are not metrizable. Okay. So let us now prove that important theorem which I am going to discuss. I discussed several times before. Now let me again tell you that if you start with this R omega or whatever the countable infinite product or RN. Okay, so this is not metrizable. So with box topology, with metrizable for box topology. Obviously for product topology we said this is metrizable, right? But for box topology it is not true. So box topology is not metrizable. So you have example where the topological space is not coming from a metric. Okay. No, any metric, not coming from any metric. Okay. Now to prove this thing, what? So we see if it is metrizable, then sequential lemma is that sequence lemma is true, right? Now we'll show that sequence lemma is false here. Okay. So prove, how do you prove that? If R omega with box topology is metrizable, then that above that just to prove sequence lemma, no, then the sequence lemma lemmas that converse part is true, right? The converse part. Okay, and so we will show that this is false. Actually the sequence lemma is false. Okay, so to show this thing, what? So you have to find out a set and a point which is inside the closure of the set, but there does not exist a sequence of the set which converges to the point, right? So let me just take the set. So let set A is considered the set. It is this infinite sequence x1, x2, okay, and such that your xi's are all positive. You choose all positive xi's. Okay, and this is for all I belongs to a natural number. Okay, so this is a set of subset of R. Obviously this is inside R omega. Okay, and we claim that there is a point which is limit point of that, but it is not a limit of any sequence. So this zero element, maybe let me write down 0 bar, which is 0, 0, 0, every point is 0. So this is obviously inside R omega, right? It can be the origin of that. Okay, so we claim that this belongs to a bar, a closure of that. This is my claim. Okay, but there does not exist any sequence which converges to x. Converges to x means x equal to 0 here. Okay, this is 0 bar. This is our claim. Now how to prove this is an element of the A closure? Now what do you need to prove? To prove something element of A closure with respect to some topology, that whenever you choose any open neighborhood of that point, it always intersect with A, right? Always intersect with A. That is the meaning of that point belongs to that closure of the set. Okay, so you choose any neighborhood. So let You choose any neighborhood, say u inside. So let me write down the like this, say a1 b1 cross a2 b2 cross a3 b3 and so on. So be a neighborhood of this 0 bar in the box topology. Okay, so these are element of box topology. Okay, so what does that mean? That means this implies 0 belongs to this neighborhood ai bi for all I, right? The 0 bar is 0 0 0 0, so everything inside this, right? So what does that mean? This implies these bi's are positive for all I, right? And hence you can talk about the point, say maybe let me write down b bar something like that, half b1 half b2 half b3. This is just example I am giving, right? So this is the point which is element of obviously a, right? Because a contains all the points whose coordinates are all positive. So bi is a positive, means bi by 2 bi by this, the half of these are positive, right? All the elements are positive. But you see that bi is, this b bar is also elements of u, right? So this b bar and b bar is also inside u, right? The open neighborhood. Given any open neighborhood, you have that element, kind of this element, right? Because this the first coordinate b1 by 2 inside the first interval, second coordinate is second interval, right? So this, so what does that mean? That means thus given any interval, any open neighborhood of 0 intersection a is always non-empty, and thus this 0 bar is element of a closure, right? This is obvious. But now I will claim that though it is a element of the closure, it is actually it cannot be a limit of any sequence. Okay, so so it cannot be limit of any sequence. So now how to prove that? So so given any sequence, the limit 0 bar cannot be the limit. So for any sequence, how it look like? So you have a sequence, say maybe let me write down the sequence by this symbol. So okay, maybe let me write down a by a, it will be easier. So a1 maybe something like that, x11 x12 x13. okay, well, why I am writing this thing? Because I just want to say that this a1 is the sequence whose elements, the coordinates are kind of x11 x12 x13, and this is the x11 is the first coordinate of a1, x12 is the second coordinate of a1. Similarly, a2 is a sequence, a2 is the element, and so the sequence will be an. Okay, this will be a sequence which is inside say a. Okay, so how do I write? Maybe this a in bar, something like that, a bar, something like that. Okay, doesn't matter. So this is what this is: x21 x22 x23 and so on. Okay, in general the nth term will be x n1 x n2 and so on. Okay, now so this is my sequence a1 of this. So I'm claiming that this sequence, whatever the sequence, whatever xi x2 whatever you choose, this sequence cannot converge to 0 bar. Okay, and why cannot converge to 0 bar? Because see, this x1 x2 x3, these are all actually element of this a1 a2 is the element of a. That means the x11 x12 x13, these are all are positive actually, right? So these xij's are always positive for all I and j, right? So I can choose a open neighborhood of 0 such that none of the elements so none of the elements actually belongs to the open neighborhood. So that means any sequence cannot be a limit, any sequence cannot converge to the point 0, right? So now let me just define open neighborhood. So let me define open neighborhood, say u dash by this symbol. So for first neighborhood I am writing minus x11 to x11. Okay, now obviously this is a neighborhood which contains 0, right? And for second one I am writing minus x22, x22, and so on, for another one minus xnn, and so on further. Now this is the element of, obviously this is the element of that box topology, right? So this is a neighborhood of 0 bar in the box topology, obviously. Topology. Okay, because this x11, x2s are positive, so minus x11 to minus plus x11 contains 0, right? So everything is contains 0. So this is open neighborhood of 0 by box topology. But you say that, you check that this neighborhood does not intersect the sequence. Why doesn't intersect the sequence? Because the first element of the sequence, a1, cannot be belongs to the neighborhood, because x11 does not belongs to this first component, right? This is open neighborhood. Similarly, the second element of the sequence does not belong to this, and so on. So an does not belongs to u dash for all n, right? So given any sequence that cannot converge to that 0 bar, because you always find out a neighborhood of 0 bar which does not contain any such element of the sequence, right? So what does that mean? That means any sequence does not converge to the 0 bar. So what does that mean? That means 0 bar cannot be limit of any sequence, right? So thus the sequence lemma fails, right? So lemma does not true in R omega with box topology, right? What does that mean? So thus thus this is not metrizable, right? Every metrizable, this has to be true, that will prove it. So this is not metrizable. Okay, so this is an example of a space where you have a topology, but the topology is not coming from any metric. Okay, so maybe this is okay, so this is the important things we just want to prove, but there are many more important idea. Maybe I just want to define it. One is called continuity, sequential criteria for continuity. Another one is for uniform convergence, okay, theorem. So this kind of uniform convergence of sequence of functions, two things. So let me prove one by one. So sequential criteria for continuity. Okay, so this is obviously, I am assuming the space is metrizable, then only I can talk about the sequential criteria. Okay, so okay, rather the range is metrizable, I don't need the codomain. Okay, so what is the theorem? So theorem tells you that, so suppose you have a function from x to y, if f is continuous, then for every sequence xn converges to x, f of xn converts to f of x. Okay, and that is true for obviously. So this is inside x, this is inside y, f of xn, right? Okay, so this is true for any topological space. Okay, but what about the converse? If we know that if given a function which satisfies this property, whether the function is continuous or not, so that is true for that metrizable space. If the space x is metrizable, then it is true. Okay, the converse is true. You don't need anything for the range space, so the converse is true if x is metrizable. So what does that mean? That means the topology of x coming from metrizable. Okay, so that means if xn converts to x implies f of xn converts to f of x, that means it has to be continuous functions. Okay, so how do you prove? So obviously proofs are not so difficult, but you need to follow the logical thing step by step. So let me just start with the condition which is given. Let a be a continuous functions and what is given, xn converts to x. So this is sequence xn is there which converts to x. Okay, so I need to prove that f of xn converts to f of x. Okay, so this is our claim. Claim is that f of xn converts to f of x. Okay, now so convergence means what? So f of xn converts to f of x means you choose a open neighborhood of f of x and so that there exists a natural number such that after that the tail of the sequence f of xn inside the neighborhood, right? So you start with the neighborhood. So let D be a neighborhood of f of x. Okay, you need to find a natural number such that this happens, right? So because neighborhood means open set containing f of x, but why f is continuous, so thus f inverse of v is open in x, right? Because this is continuous, right? Now if b is open in x, and obviously it contains and x belongs to that f inverse of b, right? So just now okay, so one more thing. So this is open set and that contains x. Okay, and so what does that mean? That means you can always find out so, and obviously you know that xn converges to x. So what does that mean? If xn converges to x and you have open neighborhood of x, then you can find a natural number. So thus there exists a natural number natural number n such that what happen, such that this the tail belongs to that thing, right? What does that mean? That means xn belongs to f inverse of v for all x, for all n greater than equal to that natural number, right? That is coming because xn converges to x and you have open neighborhood of x which is f inverse of v, and but this implies that f of xn belongs to v for all n greater than equal to natural number n. What does that mean? That means thus this sequence xn converges to fx, right? This is we want to prove, and that is now obvious, right? Okay, so now conversely, so if we assume that if the space is metrizable, then the converse part is also true. So conversely, so we are assuming that x is metrizable. Okay, and what I need to prove? I need to prove that and if x converges to x implies x converges to x. Sorry, x converges to x and converges to x implies f of x and converges to x. So this is given to me, and I need to prove that. And actually, this is a function such that what is given such that xn converges to x implies f of xn converges to f of x. And what is our claim? Our claim is that f is continuous. This I need to prove. Continuous. This is our claim, right? Now to prove something is continuous, there are so many ways to prove it, right? And you remember one way is that if you have a set, any subset of that set, and then image of the closure is belongs to the closure of the image, right? And this is one of the conditions I'm going to prove here, which is easier. Okay, so let A is subset of x. So we will show what we will show. We'll show that f of a closure is subset of f of a whole closure. Image of the closure is subset of the closure of the image. Okay, this we will show. Now to show this thing, what I need to show that you start with the element of x inside a closure and f of x inside f of a closure, right? So let you start element. So let x belongs to a closure. Okay. So because x is metrizable and you have an element in a closure, there exists a sequence xn inside A such that this xn converges to x, right? This is because x is metrizable, and this is using sequence lemma. Right? So this implies the condition inside this theorem tells you that f of xn converges to f of x. Right? For every such sequence which converges to x, f of xn converges to f of x. Right? Now f of xn converges to f of x means what? That means so this implies. Okay, so see x. Okay, so the sequence lemma tells me what? So 1 minute. Okay, so where is x? So x is inside a closure, right? And f of x is inside. Okay, so 1 minute. F of x inside y, right? Because the map is from x to y. Now f of xn converges to f of x, and that means that sequence lemma tells you that if xn converges to f, and okay, this implies f of x is actually inside f of a, as f of xn's are element of f of a, right? Because a xn is element of f of a, so f of xn is element of f of a, and not only that, sequence lemma, and using sequence lemma, right? Sequence lemma, because sequence lemma tells you that whenever f of xn converges to a point f of x, then f of x has to be inside that a closure, right? So so this is f of xn. 1 minute. What I am writing, I just want to write the f of xn converges to f of xn inside f of n, and using sequence lemma, this f of xn's are elements of xn, the limit of the sequence xn's are element of f of a closure, right? If you have a sequence of set, then the limit of the sequence belongs to the closure of the set. So f of xn belongs to this, and thus f of a closure is a subset of f of a whole closure, and hence f is continuous. Okay, this is the proof. Okay, so this is one idea of continuity inside metrizable space, that you can express it in terms of sequential criteria. And there is one or two more idea I just want to tell and say stop it for today. The other thing is called uniform convergence. So what is that? The meaning uniform convergence of sequence of functions. Okay, so what is the definition? So let we have a function fn from x to y, where x is metrizable, or rather I don't need x. I think y is enough. Where y, for x I don't need it. Y is metrizable. Okay. So, and obviously metrizable with respect to some matrix. So with respect to a metric D. Okay. So we say that y is uniform convergence to, we say this sequence f of xn is uniformly converging to a functions f from x to y if what happened? If the metric is there, if this distance from f of xn for every point to f of x is less. Okay, so this is for every epsilon positive. If for every epsilon positive there exists a natural number n, there is n such that this f of xn is less than epsilon for all n bigger than equal to this natural number n. Okay, some natural number, and for obviously this for all x. So convergence was there for there is a natural number, right? But for sequence you can have two kind of convergence. One is pointwise convergent that depend on the point, and uniform convergent that is independent of the point, and that tells you that the distance between f of xn and f of x you can make it less than epsilon after certain states. So if you cross the natural number n, then it is true for every x. So this is the meaning of uniform convergence. And in the metric space, if we have this property that y is a metric space, then you have a very nice theorem that is called uniform limit theorems. And I will just, the proof is very simple, not difficult, so I will just write down that statement and end it. Maybe you can do it at homework. So this is you have learned, I think, in already in real analysis. So I'm just writing it here. So uniform limit theorem. And what does that theorem tells you? That so this theorem tells you that image of a uniformly convergent continuous function is continuous. What does that mean? Okay, so limit. Okay, so limit of the uniformly continuous functions is continuous. That is, what does that mean? So you suppose you have these functions from x to y, and f of xn converges to f uniformly with respect to that matrix D on y. Okay, then then map f is from x to y is continuous. and the proof is not very difficult. So you just check that pull back open set is open, okay, and you use that property of metric, okay, the triangle inequality, okay, and this theorem is very common theorem you have learned in analysis probably, okay. Okay, so by that I am going to end this today's lectures, and this is metric topology and their property. Okay, there are many other things are there, but this is enough for our syllabus. Okay, so I'll stop here.